Our next speaker is Amelie Newton. She's a geophysicist who works with time domain EM data at Hudson Bay Minerals. Amelie holds an honor BSc in geological science with concentration in geophysics degree from the University of Manitoba. And she will talk about Lalor this morning.
Thank you. Today I'll be speaking on the geophysical overview of the Lalor VMS deposit. I'll start by talking about the location, the geology, the pre-Lalor discovery phase, which includes surveys that were completed before Lalor was discovered, the Lalor discovery, the post-Lalor discovery phase, which includes test surveys that were completed after Lalor was discovered, the lessons learned from the whole process, and the conclusions. So for the location, the Lalor deposit is about 8 kilometers west from the town of Snow Lake. Snow Lake is in the province of Manitoba in Canada, and Snow Lake is located about 700 kilometers from the capital city of Winnipeg. To the left, you have a simplified geology of the Flin-Flon Snow Lake Greenstone Belt. The juvenile arc rocks shown in green are the most prospective rocks. The Lalor deposit occurs within the Snow Lake assemblage, which is in the eastern part of the Greenstone Belt, and is represented by the black rectangle, and this is a blown-out figure of that. So the Lalor deposit occurs in the Snow Lake assemblage, which is about 20 kilometers wide and 6 kilometers thick, and consists of 3 volcanic sequences. So you have the Anderson sequence in green to the south in the primitive arc. You have the Chisel sequence in dark purple in the mature arc, and you have the Snow Creek sequence in light purple in the arc reef certain. The Chisel sequence is the most prospective sequence that hosts the Lalor deposit, as well as other past producing mines and deposits, such as Chisel, Lost, and Ghost mines. The Chisel sequence is divided into 2 main parts. You have the lower Chisel sequence to the bottom and the upper Chisel sequence to the top. And these are separated by what is interpreted to be a structural contact, which will be that. So the lower Chisel sequence is intensely altered and shallow deepening to the northeast, while the upper Chisel sequence is relatively unaltered and steeply deepened also to the northeast. For the local geology, the Lalor lens consists of about 14 mineralized lenses from a depth of 600 meters to about 1,480 meters. The overall strike of the geology is 320, and it deeps 30 degrees to the north. For the lateral extent, it's about 900 meters in the north-south direction and 700 meters in the east-west direction. Overall, the deposit can be grouped into 3 main groups. You have the zinc-rich lenses to the top and southernmost part of the deposit, the copper-gold-rich lenses to the bottom and northmost part of the deposit, and you have the gold-rich lenses sitting in the middle of that. So the pre-Lalor discovery phase, a brief history. The historical surveys in the area consisted mainly of EM surveys, so you had airborne surveys and borehole EM surveys. Most of these surveys were focused on depths shallower than 300 meters, and as such, the survey parameters included small transmitting loops of about 600 meters by 600 meters, high base frequencies of greater than 15 hertz, and short line lengths of about 1.5 kilometers. In 2002, 2003, the Chisel Basin was highlighted as prospective and marked for exploration. It was known that the Chisel geology was flatline, it was deep into the north, and it was getting progressively deeper, so of a vertical depth of greater than 700 meters. Based on this, it was expected that the EM response from a conductor at that depth would be a low amplitude, broad wavelength response. The Chisel Basin itself is weakly mineralized, and so moderately conductive. So this posed a challenge in being able to distinguish the EM response from the moderately conductive Chisel Basin versus the EM response from a VMS conductor at that depth. So to overcome this, the exploration groups decided that they will survey later in time using a lower base frequency. This was done to distinguish the moderately conductive response from the Chisel Basin, which would be expected to decay earlier in time, from the potential response from a VMS conductor at depth, which you expect to see later in time. Also, they decided to boost the late amplitude times by using large transmitting loops of 2 kilometers by 2 kilometers in comparison to the 600 by 600 meter loops that were previously used. And overall, to increase the data quality, they decided to stack longer. So in 2003, several kilometers of deep end were completed in the Chisel Basin area using multiple loops. The survey specs included large transmitting loops, double-tone wire, low base frequencies of 5 hertz or lower, and long survey lines of at least 3 kilometers. Based on this, 2 anomalies were identified for follow-up. You have the loop 2 anomaly to the south here, and the loop 4 anomaly to the north here. In 2003, the south anomaly was drilled by CH0305 and intersected 10 to 15% sulfides, which consisted mainly of pyrrhotite and stringer chalcopyrite. In 2005, it was decided to do a single loop time domain EM survey, which would be that loop over there, over the south and the north anomaly. This was done to clear up any misgivings that the 2003 anomalies were due to current channeling, as they were coincidentally centered on their respective 2003 loops, as you can see there. The 2005 anomaly identified both the south and the north anomaly, which proved that they weren't due to current channeling and they were actually legitimate conductors. So because the north and the south anomaly were surveyed using the same loop, it was easier to compare the north and the south anomaly because they had the same survey parameters. The figure to the right is a gridded Z component data representing a time of 2.64 milliseconds. The middle figure represents a time of 14.4 milliseconds, and the figure to the right represents a time of 37.7 milliseconds. From comparing the figures, you can see that the north anomaly is more conductive because as you go later in time, it gets stronger, while the south anomaly is less conductive because as you go later in time, it gets weaker and eventually decays away before the north anomaly. This was interpreted to mean that the north anomaly had more sulfides associated with it. Also, worth mentioning is that the north anomaly doesn't show up to this figure, which represents 14.4 milliseconds. This was used to provide justification for surveying later in time because anomalies that haven't started decaying until later in time could easily be missed if only high-frequency surveys are completed. So the north anomaly was modeled using the Maxwell 3D modeling software and models as an 800 meter by 800 meter plate at a depth of 700 meters. In 2007, this was drilled by Dub 168 and intersected over 45 meters of greater than 7% zinc and 0.3% copper, which was the Lalor discovery hole. Drilling in the area continued till about 2012, and in 2014, the Lalor mine was put into commercial production. So the post-Lalor discovery phase. To aid future exploration, Hudbay decided to characterize the geophysical response of the Lalor discovery. To do this, a number of surveys were completed over the Chisel Basin, including airborne surface and borehole surveys. The table to the right shows all the surveys that were completed and all the companies that completed the survey. Unfortunately, I can't talk about all the surveys, but in this presentation, I'll highlight the HISM survey, surface and borehole EM surveys, seismic reflection survey, and the borehole gravity survey. So the HISM system is a hybrid system between conventional airborne systems and conventional surface systems. It makes use of a large ground transmitting loop and a helicopter-towed B-field receiver system. This survey was completed over the Lalor deposit in 2014 by GAP Geophysics Australia and Discovery International Geophysics. The figure at the bottom here represents the EM profile response over one of the test lines, and it identified the Lalor deposit, which was also supported by subsequent modeling. Because this is a hybrid system, it combines the pros and the cons of both the conventional airborne system and conventional surface EM system. So some of the pros of the HISM system is the fast data acquisition, which is consistent with other airborne EM systems. It also has a large dipole moment, which it gets from the large ground transmitting loop that it uses. And with the HISM system, the B field is measured, not just calculated, which improves the overall signal-to-noise ratio. And it had the option of a lower base frequency available. In this case, a base frequency of 3.75 hertz was used in comparison to conventional airborne systems that use about 30 hertz, and just recently about 15 hertz. Some of the cons of the HISM system is that you still need to lay the large ground loop in what could potentially be a rough terrain. Also, the loop is stationary, which means you have to have a pretty good idea of what the geology is doing to be able to plan the loop to couple well with your geology. In contrast to conventional airborne systems where your loop is mobile with a helicopter and you're bound to couple with your geology at some point. Also, a minimum flight speed requirement of about 80 kilometers per hour is needed for the HISM, consistent with other helicopter-borne EM systems. However, this reduces the amount of stacking that you can have at a given station or point along the line, in contrast to conventional surface EM, where you can stack for as long as you want at a given station. And of course, for a small grid, the cost of the HISM far outweighs the cost of a conventional surface EM survey. So surface and borehole EM surveys. Several surface and borehole EM surveys were completed over the Lalor deposit using different survey parameters and different survey equipment. And most of them identify the Lalor deposit, with the major difference being in the data quality obtained from surveys that were completed using the DBDT sensor versus surveys completed using the B-field sensor. And the surveys completed using the B-field sensor provided cleaner data compared to the DBDT. So the two figures to the top are from a surface EM survey, and to the bottom you have a borehole EM survey. To the right, you have data collected using a DBDT sensor, and to the left, you have data collected using the DBDT sensor, and to the right, you have data collected using the B-field sensor. And as you can see, the data collected using the B-field sensor is a lot cleaner than the data collected using the DBDT sensor, which is noisier in the late time. The difference in the data quality could be the difference between identifying or missing the low amplitude broad wavelength response from a VMS or any conductor at depth. And also what mentioned is that because the B-field was cleaner, you could reduce the amount of stacking, which reduces survey time and thus save some cost too. So the Seismic Reflection Survey. This was completed over the Lalor deposit in 2013 as part of the TGI-4 program. To aid the interpretation of the seismic data, a 3D detailed geological model was used to do that. And the 3D geological model is shown in the colored cube in that figure. The yellow represents the felsic rocks, the green represents mafic rocks, and the yellow and green are used to show areas of the least alteration in the hanging wall and in the footwall rock. The purple is used to show the area of intense alteration in the footwall, and that's a felsic unit. And the red represents the Lalor deposit. So overall, the hanging wall was devoid of seismic reflections, while the footwall showed a higher number of and stronger reflections. In the footwall, the zinc-rich lenses produce strong reflections due to the high impedance contrast with their host rock, while the copper gold and the gold-rich lenses produce weak to no reflection due to the low impedance contrast with their host rock. And overall, the most common reflection was between the mafic and the felsic rocks, regardless of the degree of alteration. Some important or noteworthy reflections are labeled A to D in the figure. A is the continuation of the contact between the felsic and the mafic rocks in the hanging wall. B is the continuation of the contact between the mafic volcanic rocks in dark green and the mafic volcaniclastic rocks in a lighter green. Reflection C is the continuation of the contact between the intensely altered felsic rocks in the footwall and the mafic rocks in the hanging wall. And this could be used as a proxy for the structural contact between the lower Chisel sequence and the upper Chisel sequence. And the ability to follow this contact in 3D is really important because the Lalor deposit, as well as other past producing mines in the area, occur at or near this contact. Reflection D is interpreted to be the base of the Chisel sequence at the contact with the Anderson sequence. And from the north-south cross-section, which is represented by this red line, you can see that the reflection D suggests that the Chisel sequence folds back up to surface to the north, which could put it at a shallower, more economic depth to the north, which would be right about here. So the borehole gravity survey. This was completed in 2014 as part of the TGI-4 program. 5 NQ holes were surveyed, which were around the Lalor deposit and at least 250 meters away. Unfortunately, there weren't any holes closer than 250 meters because they had all been cemented so as not to interfere with underground mining. Overall, the borehole gravity survey identified areas of increase in density, which correlated mostly with mafic rocks. For example, in the figure in the middle, which represents the data from DUB 279, the highest density is 3.1 grams per centimeter cubed at a depth of about 840 meters. And this corresponded with the intersection of pyrrhotite in mafic tuff, which also showed no significant assays. Because of the distance of the holes from the Lalor deposit, so greater than 250 meters, a case could be made for a potential long wavelength future from a depth of about 400 meters to 900 meters, with shorter wavelength futures superimposed on and distorting this long wavelength future. However, without the knowledge of the Lalor deposit being there wouldn't have been enough confidence to drill that potential long wavelength future to detect the Lalor deposit. So a number of lessons were learned from the Lalor discovery process, and a few of them will be highlighted here. The first one is the importance of geology. Geology is important in the planning and in the interpretation phase. For the Lalor example, without the knowledge that the Chisel Basin was flat-lying, dipping to the north and getting progressively deeper as you go north, historical survey parameters such as small transmitting loops of about 600 meters by 600 meters, high base frequencies, and short line lengths would have been used and would not have been sufficient or may not have been sufficient to detect the Lalor deposit. The second one is data integration. Some of the surveys, when looked at as standalone data, did not confidently detect the Lalor deposit. However, when integrated with other geophysical and geological information, they provided another piece to the Lalor puzzle. The third one is the limit of available data. It's important to know the limit of your data because areas that appear tested on surface or plan maps may not be adequately tested at depth. Figure A shows the plan map of the Lalor deposit, so you have the Lalor outline here. And it shows other mines, previous mines and zones in the area, kind of in red. Figure B shows the same map, but overlain with pre-Lalor geophysical grids. Figure C is the same map, but it has the pre-Lalor geophysical grids and the pre-Lalor drill holes. The green circles represent holes that are shallower than 500 meters, and the yellow circle represents holes that are deeper than 500 meters. When you look at figure C, it appears that this area has been really explored by both the surface geophysics and by the drill holes. However, when you look at the surveys that would have seen deeper than 500 meters and the holes that are deeper than 500 meters, you see that most of the holes deeper than 500 meters are in areas of known deposits or zones. So in that case, it opens up a whole lot of area to be able to find another Lalor-type deposit. And last but not the least is the importance of EM survey line length. This is a simple lesson learned, but was worth mentioning using the Lalor example. To the right, you have a 1 kilometer section of line over the Lalor deposit. And when you look at that data, it just looks like elevated background noise with no significant anomaly. To the right of that, you have a 3.5 kilometer line over the same area, but now you can start to make out the response of the Lalor deposit. So it's important that for flat-line conductors to make sure that your line lengths are long enough to be able to record the full response from the deposit. So in conclusion, several surveys were completed over the Lalor deposit. The EM surveys produced the most prominent response in direct correlation to the Lalor deposit. From the EM surveys, the B-field data collected with the B-field sensors were a lot cleaner than the DBDT sensor. From the seismic survey, the zinc-rich lenses of the Lalor deposit produced strong reflections due to the high impedance contrast with your host rock, while copper gold and gold-rich lenses produced weak or no reflections. Overall, the most common reflection was between the mafic and felsic rocks, regardless of the degree of alteration. From the gravity survey, area of increase in density was identified, which corresponded mostly with mafic rocks. And the key lessons learned from the Lalor discovery process was the importance of geology, the importance of data integration, and the importance of knowing the limits of your data. And thanks for having me here today. Thanks for listening to the talk. And I want to thank everyone that contributed to the paper and this presentation. Thanks.
Hang on. Neme, we got time for a couple of questions because this session is actually straddling through to lunch where the other ones are broken up. We've got about over 10 minutes before the what we call the part 2 is starting, which will be at 10:40. So, to the point, if you have any questions for Neme, please, we have some time to throw them out. Apologize to the other authors. It's when we turned the page, we said, oh, okay, we've got some time.
I should have gone longer. Yes, the ore is conductive. We do take mag sauce and conductivity readings, and it's conductive. Even though it's zinc rich, it does have enough pyrrhotite in the ground mass that makes it conductive.
Just one thing, as people are drifting away, there was 2014, a 2-day session. As Neme's list showed, there was an incredible amount of work done here, and there were a series of presentations spent over 2 days by the BCGS. Those recordings are on the DMEC site, so it's dmec.ca under resources, and we have the full set. So far more,
Really
than you
stuff.
can present in 20 minutes. Yeah, so there you go.
Yeah.
Anything else? A question in the back?
A lot of it, like my figures show, does this still work? But I had one of those figures, and you can see that when you took out the geophysical grids that could see deeper than 500 meters, and the drill holes that were deeper than 500 meters, there was a lot of open area. Most of the deep drill holes are concentrated in areas of known deposits and zones already, so there's lots of open ground to find something, to explore and find something new.
I do have one question. You showed the EM plan map where you have that northern anomaly and the southern anomaly, and the one to the south disappear with time because it's less conductive, and the one to the north remains later in time. But knowing that Lalor is a zinc-rich deposit also, were you able to make a correlation with the nature of the sulfides themselves?
Yeah, so it's zinc-rich. But it does have a lot of pyrrhotite in the ground mass, like
Okay.
when you look at the lenses that are really conductive.
Yeah.
And also you have the copper gold rich lens to the bottom. It's pretty deep, but it's really conductive, that one too.
Okay.
So I think together that's why they have
It's pushing the conductance
the conductivity
higher.
high, yeah,
Okay.
even though it's zinc rich mostly.
Okay, thanks again, Neme.
Thank you.
Appreciate it. Okay. So it's about 10 minutes.
Yep, we have 10 minutes.
And we'll be back at 10, okay?